New data from the James Webb Space Telescope is pointing at a small, rocky world called TRAPPIST-1e. And what Webb is seeing is not what most people expected. By the end of this video, you'll understand why some scientists are calling it the closest thing to Earth we've ever found, and why that claim might be both exciting and risky. TRAPPIST-1e sits about 40 light years away from us. That sounds far, but in space terms, it's right next door. If you could drive a car to it, which you can't, it would take longer than the entire history of human civilization. Still, for astronomers, 40 light years is close enough to study with real detail. The planet orbits a small red dwarf star called TRAPPIST-1, a star so cool and dim that all 7 of its known planets huddle close to it, like people crowding around a campfire on a cold night. TRAPPIST-1e is the one planet in that system that sits in what scientists call the habitable zone. That's the narrow ring where temperatures could allow liquid water to exist on the surface, not boiling away into steam, not freezing solid into ice. It doesn't mean there is water. It means water could survive there if the right conditions exist. That alone makes TRAPPIST-1e special. Out of thousands of exoplanets discovered so far, only a small handful are rocky, roughly Earth-sized, and in the habitable zone of their star. The first time astronomers realized how interesting this system was, it was thanks to the TRAPPIST telescope in Chile, followed by work from the Spitzer Space Telescope and later the Hubble Space Telescope. Teams connected to NASA's Jet Propulsion Laboratory helped refine the orbits and sizes of these worlds, turning blurry dots into real planets with names and numbers. TRAPPIST-1e stood out early because of its size. It's almost the same size as Earth. Its mass suggests it's rocky, not a gas world like Neptune. That's the first box it ticks. Then James Webb came into the picture. The James Webb Space Telescope does something that older telescopes struggle to do well. It doesn't just take pictures. It studies light in fine detail. When a planet passes in front of its star, a tiny bit of starlight passes through the planet's atmosphere before reaching us. That light carries fingerprints of whatever gases are in the air. Scientists call this transmission spectroscopy. It's like shining a flashlight through smoke and guessing what's burning by the color of the light that comes out. When Webb watched TRAPPIST-1e pass in front of its star, researchers from teams working with NASA, the European Space Agency, and universities like the Harvard-Smithsonian Center for Astrophysics began to pull apart that light. The first big result surprised many people. They ruled out thick, fluffy atmospheres made mostly of hydrogen and helium. That's good news for life. Those kinds of atmospheres belong to mini gas giants, not Earth-like worlds. They also ruled out a Venus-style thick blanket of carbon dioxide that would trap heat and turn the planet into a pressure cooker. They even ruled out a thin, Mars-like atmosphere that would struggle to hold heat and water. What was left on the table was the most interesting option. An atmosphere more like Earth's, mostly nitrogen, with smaller amounts of water vapor, carbon dioxide, maybe methane. Not proof of life, not even proof that the atmosphere exists. But the data lines up with the kind of air that could support liquid water and stable weather. That's where the headline numbers start to appear. Some models, based on what Webb can and cannot see, suggest a very high chance that TRAPPIST-1e has a secondary atmosphere, one built by volcanic gases and geological activity rather than leftover gas from the planet's birth. That's where people throw around numbers like 99% chance. Those numbers are not magic. They depend on models and assumptions, but they tell us something simple. Among the planets we've studied so far, TRAPPIST-1e fits the profile of a potentially livable world better than almost anything else. Now comes the part where the story gets complicated. TRAPPIST-1e orbits a red dwarf star. Red dwarfs are small and cool, but they're also loud in another way. They throw tantrums. Powerful flares blast out radiation and charged particles. Early in their lives, red dwarfs can strip the atmospheres off nearby planets. Astronomers using data from observatories like the European Southern Observatory and older radio surveys inspired by work once done at Arecibo have shown that red dwarfs can be violent for billions of years. That's a problem for life. Radiation can break apart molecules and blow away air. On top of that, TRAPPIST 1e is tidally locked. One side of the planet always faces the star. The other side is an endless night. Imagine standing on a world where the sun never moves. One half of the planet bakes, the other freezes. That sounds hostile. But climate models run by teams working with NASA, JPL, and universities show something interesting. If the planet has a thick enough atmosphere, winds can carry heat from the hot side to the cold side. Instead of one side being a desert and the other a glacier, you could get a band of mild climate around the edge between day and night. Scientists call this the Terminator Zone. It's a strip of endless twilight. Not too hot, not too cold. If life could take hold anywhere on a tidally locked world, that's where it might settle. There's another layer to this. TRAPPIST-1e may have internal heat. The planet is tugged by the gravity of its neighbors as they all orbit close together. That tugging can stretch and squeeze the planet, heating its interior. This is called tidal heating. We see the same thing in moons like Europa and Enceladus in our own solar system, which have warm subsurface oceans under thick ice. Scientists studying data from missions tracked by NASA, JPL, and older Voyager 1 telemetry have seen how tidal forces can keep worlds warm long after they should have cooled. If TRAPPIST-1e has a molten core, it could drive volcanoes, release gases to build an atmosphere, and even create hydrothermal vents under oceans. On Earth, hydrothermal vents are packed with life, even though no sunlight reaches them. This raises a strange idea. Life on TRAPPIST-1e, if it exists, might not look like forests and oceans under blue skies. It might live in a dim strip of twilight, or under ice, or near hot vents in a global ocean hidden beneath clouds. Life does not need sunshine the way plants on Earth do. It needs energy, chemistry, and time. Time is the quiet hero in this story. Red dwarf stars live a long, long time. Not millions of years, trillions. The universe itself is only about 13 billion years old. TRAPPIST-1 will keep shining long after stars like our sun burn out. That gives any life on TRAPPIST-1e an enormous window to get started, stumble, adapt, and grow complex. Even if early flares stripped away early atmospheres, the planet could rebuild its air over and over through volcanic activity. Over billions of years, small chances add up. This is why TRAPPIST-1e is called the single most promising Earth-like world we've found so far. Not because it's Earth 2, but because it sits at the intersection of size, temperature, chemistry, and time in a way that few other worlds do. We are still at the beginning of this story. James Webb is scheduled to watch TRAPPIST-1e pass in front of its star many more times. Each transit adds more detail. 15 more transits are planned to build a clearer picture of what gases might be present. If Webb detects carbon dioxide clearly, that would confirm a secondary atmosphere. If it detects methane alongside carbon dioxide, that combination becomes interesting because on Earth, those gases are often linked to life. If Webb detects water vapor, that would be historic. It would mean we have direct evidence that water is present in the air of a rocky planet, in the habitable zone of another star. None of that proves life. But it would move TRAPPIST-1e from interesting to extraordinary. And here's the part many people miss. Even if TRAPPIST-1e turns out to be lifeless, the process of finding that out teaches us how to read other worlds. The James Webb Space Telescope, backed by decades of groundwork laid by Hubble, ground observatories like Keck in Hawaii, and theoretical work done at places like the Harvard-Smithsonian Center for Astrophysics, is building a new way of looking at planets we can never visit. We're learning to smell the air of worlds we will never touch. That is a new chapter in human history. Here's the part most headlines skip. Even if TRAPPIST-1e sits in the habitable zone, and even if James Webb is hinting at an Earth-like kind of air, that does not mean the planet is friendly to life. In fact, it may be one of the harshest places you could imagine trying to stay alive. The same star that gives it warmth also throws violent flares. The same close orbit that keeps water from freezing may also keep the planet locked in endless daylight and endless night. The question isn't just, can life exist there? The question is, can life survive there long enough to get started at all? Red dwarf stars are strange parents. They are small and cool compared to stars like our sun, but they behave like toddlers with fireworks. Early in their lives, they throw huge magnetic storms. These flares blast out radiation that can strip atmospheres from nearby planets. Astronomers working with data from the European Southern Observatory and long-term surveys informed by old Arecibo radio studies have shown that planets orbiting close to red dwarfs are hit again and again by these storms. If TRAPPIST-1e had been born with a gentle, Earth-like sky, it may have lost it more than once. So why isn't it just a bare rock now? This is where the story gets interesting again. TRAPPIST-1e is packed into a tight family of planets. They tug on each other as they move around their star. Those tugs stretch and squeeze the planet's interior, warming it from the inside. Scientists call this tidal heating. Teams at NASA's Jet Propulsion Laboratory have used similar models to explain why moons like Europa and Enceladus still have warm oceans under ice, even though they sit far from the sunday. Heat from the inside can drive volcanoes. Volcanoes can release gases. Gases can rebuild an atmosphere that was once blown away. Now add a molten iron core to that picture. If TRAPPIST-1e has one, it could generate a magnetic field. A magnetic field acts like a shield. It deflects charged particles from stellar flares the same way Earth's magnetic field protects us from the worst of the sun's tantrums. Without it, our atmosphere would slowly leak into space. This is one reason Mars lost much of its air. Mars's magnetic field faded. The sun's wind did the rest. We don't know if TRAPPIST-1e has a magnetic field, but its size and density make it possible. Not guaranteed, possible. And in the search for life, possible is a big word. There's another twist people often miss. Radiation is not just a villain in the story of life. In small doses, radiation can help drive chemistry. Some lab studies show that ultraviolet light can help form the building blocks of RNA. That's one of the paradoxes of life. Too much radiation kills. A little bit can help kickstart complex chemistry. TRAPPIST-1e star may have been violent early on, but over billions of years, its flares calm down. That creates windows where chemistry can get interesting without being wiped out over and over. Now think about the planet's strange day and night. TRAPPIST-1e is tidally locked. One face always looks at the star. One face never sees it. That sounds like a nightmare. But climate models run by researchers at the Harvard-Smithsonian Center for Astrophysics and other universities show that if the planet has enough air, winds can carry heat around the globe. The hottest place may not be the center of the day side. The coldest place may not be the center of the night side. Instead, the most stable region could be the thin ring between them, the terminator zone, a band of endless dawn and dusk where temperatures stay mild and winds bring moisture from the bright side to the dark side. Picture that. A world with a glowing side, a frozen side, and a soft, dim strip where clouds roll in slow circles and rain falls forever. If life were trying to take hold, that strip might be its safest home. But water is still the key. Webb's early data has not yet confirmed water vapor in the atmosphere of TRAPPIST-1e. It has ruled out thick hydrogen skies and Venus-like blankets of carbon dioxide. It suggests the air could be more Earth-like. That's a narrow doorway. To step through it, Webb needs more data. That's why those 15 additional transits matter. Each transit is another chance to read the planet's air like a barcode. Carbon dioxide would show up as a clear signal. Methane would show up too. Nitrogen is harder to see directly, but its presence can be inferred from what isn't there. If water vapor appears in those future spectra, that would be one of the biggest moments in modern astronomy. Not because it proves life, but because it proves a rocky planet in another star's habitable zone has water in its air. That means water is not rare. It means wet worlds may be common. Now take this one step deeper. Even if TRAPPIST-1e has no oceans on its surface, it might still hide water underground. Tidal heating could keep a subsurface ocean warm beneath ice, just like Europa and Enceladus. On Earth, life thrives around hydrothermal vents on the ocean floor. No sunlight, just heat and chemistry. Scientists working with data from NASA, JPL, and older Voyager 1 measurements of radiation environments have shown that energy from inside a world can support ecosystems without any help from the Sunday. That means TRAPPIST-1e doesn't need blue skies and beaches to be alive. It could host life in the dark, quiet, hidden, out of sight of any telescope. This is where the search for life gets humbling. We keep looking for Earths, because Earth is what we know. But life does not care what we know. Life cares about energy, liquid water, and time. TRAPPIST-1e may offer all three in ways that look nothing like home. The problem is that we can't land there. We can't drill into its ice. We can't scoop its oceans. All we have is light. A thin ribbon of light filtered through an atmosphere 40 light years away. From that, teams working with James Webb, building on decades of work from Hubble, and ground observatories like Keck, are trying to tell whether this distant world could be alive. That is a small miracle in itself. And it's also why the stakes feel so high. Even with all the hopeful signs, there's a heavy truth sitting in the background. We might be asking the wrong question. Instead of asking, is TRAPPIST-1e like Earth? We may need to ask, can life adapt to a place nothing like Earth at all? Because this world is not just a slightly warmer or cooler version of home. It lives under a red sky, around a small, dim star that flickers and flares in ways our sun does not. One of the biggest worries is atmospheric loss. Over billions of years, repeated stellar flares can peel away a planet's air like layers of paint in the sun. Astronomers using data from the European Southern Observatory and models refined with help from NASA's Jet Propulsion Laboratory have shown that close-in planets around red dwarfs are at constant risk of losing their skies. If TRAPPIST-1e lost its atmosphere early, it would have needed a way to rebuild it again and again. Volcanoes could do that, so could impacts from icy bodies that deliver water and gas. But rebuilding is slow, and flares don't wait politely. This leads to a quiet race. Can the planet build air faster than the star strips it away? That race depends on how active the star is now. TRAPPIST-1 is old, very old. Red dwarfs can burn for trillions of years, but their worst tantrums come early in life. Over time, they calm down. The TRAPPIST-1 system has had billions of years to cool into a quieter phase. Astronomers tracking stellar activity with ground observatories and space data have found that older red dwarfs flare less often and less violently. That gives planets like TRAPPIST-1e long, calm stretches to hold on to air and water. Another worry is the planet's gravity. Gravity is what helps a planet keep its atmosphere. TRAPPIST-1e is close to Earth in size and mass, which is good news. It's heavy enough to hold onto lighter gases like nitrogen and oxygen. Mars, by comparison, is smaller and lost much of its air because it couldn't grip it tightly enough once its magnetic field weakened. TRAPPIST-1e, if it has a molten core and a magnetic field, could hold onto its air far better. Then there's the question of weather. On a tidally locked world, weather doesn't look like ours. You don't have a spinning planet with day and night sweeping across oceans and continents. You have one side always facing the star. Climate models, run by teams connected to the Harvard-Smithsonian Center for Astrophysics, show that winds could move heat from the hot side to the cold side in steady rivers of air. Storms might circle the planet in giant loops. Clouds might hang over the same regions forever. Rain might fall in one place for years at a time. This could sound hostile, but stable patterns can also be good for life. Life likes consistency. If the Terminator zone stays mild for millions of years, ecosystems could adapt to that narrow band and thrive there, even if the rest of the planet is harsh. Think about places on Earth that look unlivable at first glance. Hot springs, deep sea vents, acidic lakes. Life finds a way in all of them. Not because the place is gentle, but because life is stubborn. There's another idea that sounds strange, but matters. Even if the surface of TRAPPIST-1e is battered by radiation, life might live underground. Rock and ice are good shields. On Earth, microbes live kilometers below the surface, feeding on chemical energy. On Mars, scientists look for life underground because the surface is too harsh. On Europa and Enceladus, scientists expect any life to be hidden beneath ice. TRAPPIST-1e could follow the same pattern. A harsh surface, a calmer world below. James Webb can't see underground. It can't see oceans beneath ice. All it can do is read the air. But the air is still a clue. If Webb sees water vapor that hints at water below, if it sees methane alongside carbon dioxide, that raises questions about chemistry that is out of balance. On Earth, life keeps our atmosphere in a strange mix that shouldn't last long without constant renewal. Detecting that kind of imbalance on another world would be a huge deal. Not proof of life, but a reason to pay very close attention. This is where the phrase 99.7% chance of life becomes dangerous if it's taken the wrong way. That number doesn't mean there is life there. It means that based on what we know so far, TRAPPIST-1e fits the profile of a planet that could support life better than almost any other world we've found. It's a statement about potential, not a guarantee. Headlines love certainty. Science lives on careful language. The careful language is this: TRAPPIST-1e is the best target we have right now for learning how common habitable worlds might be. It's a test case. If a planet like this has no air, no water, and no signs of stability, then truly Earth-like worlds might be rare. If a planet like this does have stable air and water, then the galaxy may be full of places where life could get started. That's why this single, small planet 40 light years away carries so much weight. It's not about finding aliens tomorrow. It's about learning whether the conditions that made life possible here are freak accidents or common outcomes of planet formation. And that answer will shape how we see the universe for generations. There's a quiet tension in this search that most people don't notice. Every time we point James Webb at TRAPPIST-1e, we're not just collecting data about one planet. We're testing an idea about the universe, the idea that life-friendly worlds are common, the idea that Earth is not a lucky fluke. The telescope is not just looking outward, it's holding up a mirror to our hopes. One of the reasons this planet matters so much is because of how hard it is to study. TRAPPIST-1e is tiny compared to the star it orbits, and the star itself is small and dim compared to our Sunday. That makes the signal faint. The light that passes through the planet's atmosphere during a transit is a thin slice of a thin slice. It's like trying to smell perfume through a closed door from across the street. This is why the James Webb Space Telescope matters. Its mirror is huge. Its instruments are tuned to the infrared, where molecules like water and carbon dioxide leave clear marks. Hubble gave us the first hints. Webb is giving us the first real measurements. Even then, the measurements are hard. A single transit does not tell the full story. The star itself has spots and flares that can mess with the light signal. Teams working with Webb and with ground observatories like Keck in Hawaii have to separate what belongs to the star from what belongs to the planet. It's slow work. It's careful work. One bad assumption can make a planet look dry when it's wet, or cloudy when it's clear. This is why those 15 additional transits matter so much. Each one is another puzzle piece. When you stack enough pieces, patterns emerge. Carbon dioxide has a clear fingerprint. Methane has another. Water vapor leaves its own marks. Nitrogen is shy and hard to catch, but scientists can infer its presence when other gases appear in certain ratios. Teams at NASA's Jet Propulsion Laboratory help run the models that turn those faint signals into real estimates of what the air might be made of. And here's a twist that surprises people. Clouds can hide life-friendly signs. A planet with thick clouds can look boring in the data. The clouds block light. They smooth out spectral features. Venus is a great example. Thick clouds hide what's going on below. If TRAPPIST-1e has global cloud cover, Webb might struggle to see the full story. That means a lack of clear signals does not always mean a lack of interesting chemistry. Sometimes it just means the planet is wearing a coat. There's also the question of how stable this planet has been over time. Life needs not just the right conditions, but long stretches of stability. The TRAPPIST-1 star is ancient. That gives its planets a long runway. But the early years were likely brutal. Flares, radiation, strong stellar winds. The fact that TRAPPIST-1e might still hold on to air today suggests it either had strong protection early on or rebuilt itself again and again. Both stories are interesting. Both tell us something about how tough life's playgrounds might need to be. This is where comparisons to our own solar system help. Mars sits in what used to be the sun's habitable zone. Long ago, it had rivers and lakes. It lost much of its air and water when its magnetic field faded. Venus likely had oceans early on, then turned into a pressure cooker. Earth kept its air and water because it had the right mix of gravity, geology, and magnetic shielding. TRAPPIST-1e sits somewhere in that same story arc. We don't yet know whether it will end up in the Mars box, the Venus box, or a box we haven't named yet. Teams at the Harvard-Smithsonian Center for Astrophysics often talk about this as a kind of cosmic experiment. The TRAPPIST-1 system is like a natural lab. 7 rocky worlds, all close to the same star, formed from the same material. Some are too hot, some are too cold. One sits in the sweet spot. By comparing them, scientists can learn how small changes in orbit and distance change a planet's fate. That's something we can't do easily in our own solar system, because our planets are so spread out and so different. The more we learn about TRAPPIST-1e, the more we realize how many things have to line up for a world to stay gentle enough for life. It's not just distance from a star. It's the star's behavior over billions of years. It's the planet's mass, its magnetic field, its geology, its ability to move heat around. It's luck in avoiding catastrophic impacts at the wrong time. Habitability is not one switch you flip. It's a web of small conditions that have to hold together. That web is fragile, but it's also resilient in surprising ways. Life on Earth has survived ice ages, asteroid impacts, supervolcanoes, and long periods when the planet looked nothing like it does today. If life can adapt here, it might adapt in stranger places too. TRAPPIST-1e may not look friendly by Earth standards, but Earth itself has not always looked friendly by today's standards either. The question that hangs over all of this is simple and heavy at the same time. Is Earth special because life is rare, or because we haven't looked long enough at the right kinds of worlds yet? There's a moment that often hits scientists working on worlds like TRAPPIST-1e, and it's not the moment of discovery, it's the moment of waiting. The waiting for the next transit. The waiting for the next clean slice of starlight to pass through that thin ring of air 40 light years away. Space does not rush for us. It moves on its own clock, and that slow clock shapes how we learn. James Webb circles far from Earth, but its work is tied to people on the ground. Teams at NASA's Jet Propulsion Laboratory, engineers who help design Webb's instruments, and astronomers at places like the Keck Observatory and the European Southern Observatory all feed into the same effort. The data comes in, and then it sits for months as people argue gently over what it means. Not arguments like fights, arguments like chess games. If this, then that. If the signal shifts here, what does that say about clouds there? If the star flares at this moment, how much does it change what we think we saw from the planet? One of the hardest parts is separating the planet from its star. TRAPPIST. One is small, but it is active. Star spots rotate in and out of view. Flares spike and fade. Those changes can look like changes in the planet's atmosphere if you're not careful. This is why multiple transits matter. Noise averages out. Patterns remain. Scientists working with Webb and with older Hubble spectrograph records compare transits months apart to see what stays the same. What stays the same is more likely to be real. There's also the challenge of not fooling ourselves. The desire to find life is strong. It's human. But desire can bend interpretation if you're not careful. Teams at the Harvard-Smithsonian Center for Astrophysics talk openly about this risk. It's why they push for blind analysis methods, where people analyze data without knowing which planet they're looking at until after the methods are locked in. That reduces the chance of seeing what you want to see instead of what is there. This slow, careful process can feel boring from the outside. People want headlines. They want a yes or no. But the truth is, the universe doesn't care about our appetite for fast answers. It reveals itself in pieces. There's another layer to the story that feels almost philosophical. Even if TRAPPIST-1e is lifeless today, it may not always have been. Planets change, atmospheres come and go, oceans can freeze or boil away. A world could have had life for 1 billion years and then lost it. From our point of view, catching that world in its living phase would be pure luck. We might be late to the party or early, or arrive long after the music stopped. This makes the search feel both hopeful and humbling. Hopeful because life might be common. Humbling because our window to see it may be narrow. The long life of red dwarf stars adds another twist. TRAPPIST, one will outlive our sun by orders of magnitude. That means TRAPPIST-1e has an unimaginably long future ahead of it. Even if the planet is harsh now, it may grow gentler over time as the star calms further. Life could arise later, long after humanity is gone. The universe is patient. We are not. This shifts how we think about success in the search for life. Finding a planet that is alive right now is a high bar. Finding planets that could host life at some point over trillions of years is a lower bar. TRAPPIST-1e fits that second category very well. It sits in a zone where water could exist. It may have internal heat. It may have air. It has time, lots of time. The role of James Webb in this story is not to deliver a final answer in one dramatic image. It is to build a case slowly, to show us what kinds of air small rocky planets can hold around red dwarfs, to show us how often water vapor might appear, to show us whether Earth-like atmospheres are rare or common. That knowledge will shape where future telescopes look and what kinds of worlds future missions target. Projects already being planned, informed by work at NASA, JPL, and observations from Webb, aim to build even more powerful space telescopes that can directly image nearby Earth-sized planets. The Vera Rubin Observatory on the ground will help find more targets by mapping the sky in detail, spotting small changes that hint at transiting worlds. Each tool adds another piece to the puzzle. TRAPPIST-1e is not the end of the story. It's the first chapter of a new kind of story, one where we stop guessing about distant worlds and start reading their skies like weather reports. And just like weather reports, the first ones are often wrong in small ways, but over time, patterns emerge. There's a quiet shift that happens when you spend years thinking about a world you will never see with your own eyes. TRAPPIST-1e becomes less like a dot on a chart and more like a place. Not a place you can visit, but a place your mind keeps returning to. Scientists start talking about it the way sailors once talked about distant islands they had only heard of, with care, with caution, with a strange kind of respect. Part of that comes from how personal the search for life really is. When we look for life out there, we're really asking why life happened here. Why this rock, at this distance, from this star, with this mix of air and water, became alive. Every promising planet we find makes that question feel less lonely. Every harsh result reminds us how fragile the chain of events that led to us really was. TRAPPIST-1e sits at a crossroads in that question. It is similar enough to Earth to make the comparison meaningful. It is different enough to remind us that life does not need to follow our exact blueprint. If life exists there, it may have no forests, no oceans with waves you can surf, no blue sky. It may live under clouds or ice or in the long shadow between day and night. That stretches our imagination. It also stretches our science because our instruments and models are built around what we know. This is where old data quietly helps new discoveries. Hubble's spectrograph records taught astronomers how to tease faint signals out of starlight. Ground observatories, like Keck in Hawaii, taught them how to track tiny dips in brightness and correct for Earth's own atmosphere. Even legacy radio data from Arecibo shaped how scientists think about separating real cosmic signals from noise. All of that groundwork feeds into how James Webb's data is read today. Science is not one telescope having a moment. It's a long chain of tools and people building on each other's work. There's also a human side to the work that rarely makes it into documentaries. Researchers worry about being wrong in public. A single overconfident claim can haunt a career. That's why most teams speak carefully. They talk about probabilities, they talk about ranges, they talk about what the data cannot yet tell us. This caution is not weakness, it's discipline. That discipline matters because the stakes are high. If Webb ever detects a mix of gases that looks like it's being constantly renewed, that would be one of the strongest hints of life we could get without leaving our solar system. It would not be proof, but it would be enough to change how future missions are designed. It would change what we tell our kids about how alone we might be. There's also the chance that Webb will find nothing but silence in the air of TRAPPIST-1e. No water vapor, no clear carbon dioxide, just a thin, stripped atmosphere or none at all. That result would be just as important. It would tell us that even planets in the habitable zone of red dwarfs struggle to hold on to the conditions life needs. That would shift the focus of the search toward planets around stars, more like our Sunday. It would narrow the field. It would make Earth feel rarer. This is the strange beauty of the search. Both answers teach us something. Both answers matter. There's a story people tell about early explorers. They would sail for months with no land in sight, guided only by the stars. Sometimes they found nothing. Sometimes they found new continents. The act of looking changed how they saw the world, even when they came back empty-handed. In a small way, James Webb is doing the same thing. It's sailing through the infrared, guided by faint signals, not knowing what it will find next. TRAPPIST-1e is one of its most tempting destinations. Not because it promises a crowd of aliens waving hello, but because it promises a hard truth about how common or rare life-friendly conditions might be. That truth may be comforting, it may be unsettling. Either way, it will shape how we think about our place in the galaxy. And that, more than any single detection, is why this tiny planet matters so much. At some point in every long search, the question changes. It stops being, what might we find, and becomes, what will we do with whatever we find? TRAPPIST-1e forces that shift earlier than most targets because it sits so close to the line between hope and doubt. If James Webb eventually shows strong signs of water vapor and a stable mix of gases, the next step will not be to shout that life has been found. The next step will be to check every possible non-living explanation. Could volcanoes alone produce the mix? Could chemistry driven by sunlight do it without biology? Could impacts from comets refresh the gases over and over? Teams at NASA's Jet Propulsion Laboratory already build models to test these scenarios, because that's what protects science from fooling itself. The more extraordinary the hint, the harder it gets tested. This testing can take years. A single promising spectrum does not change textbooks. Patterns across many worlds do. TRAPPIST-1e is a starting point, not a finish line. If similar atmospheres show up on many rocky planets around red dwarfs, the case for common habitability grows stronger. If TRAPPIST-1e looks special and others look barren, then we learn that habitability is rare, even under similar conditions. There's also a deeper issue that rarely gets airtime. Even if life exists on TRAPPIST-1e, it may be simple life. Microbes, single-celled organisms, the kind of life that dominated Earth for billions of years before anything like animals appeared. That kind of life is harder to detect from afar because it does not reshape a planet's atmosphere as strongly. The Earth's oxygen-rich air is a loud signal of life, but oxygen took a long time to build up here. TRAPPIST-1e may be alive and still look quiet. This changes what counts as success in the search. Finding complex life quickly is unlikely. Finding worlds where simple life could exist is the realistic goal. TRAPPIST-1e sits right in that window. It may be a place where life is possible, but invisible to our current tools. There's also the matter of perspective. 40 light years is close in cosmic terms, but it's still far beyond any travel we can imagine. Even if we confirmed life there tomorrow, it would not change daily life on Earth in a practical way. No ships would launch. No messages would be sent. The change would be internal. The story we tell ourselves about being alone would crack. That crack would spread slowly through schools, through culture, through the quiet way people look at the night sky. The idea that life could arise elsewhere changes how we think about how fragile and precious it is here. It doesn't make Earth less special. It makes Earth part of a larger story. This is why scientists are careful not to oversell. The emotional weight of this search is heavy. People project hopes and fears onto these distant worlds. Some want proof we're not alone. Some fear what that might mean. The role of science is not to feed either side. It is to measure carefully and speak honestly about what those measurements mean and what they do not mean. TRAPPIST-1e is teaching us how to sit with that tension, to hold hope without turning it into certainty, to accept doubt without turning it into despair. In a way, this planet is already changing us, not by giving us answers, but by teaching us how to ask better questions. As the observations pile up over years, TRAPPIST-1e slowly becomes part of a bigger pattern instead of a lone mystery. The search for life doesn't hinge on one world forever. New targets appear. New data reshapes old ideas. What stays constant is the method. Careful watching, careful doubt, careful hope. One of the quiet revolutions happening in astronomy right now is how we handle uncertainty. Older eras of science often waited for near certainty before making big claims. Today, with tools like James Webb, we live in a world of probabilities. This planet is likely rocky. This atmosphere is likely thin. This chemistry is likely stable. Likely becomes a working language. It's not perfect, but it's honest about what we can and cannot know from light alone. TRAPPIST-1e sits in the middle of this new way of knowing. The planet is not a cartoon Earth. It's not a blue marble with clouds and oceans we can see. It's a small, dark body passing in front of a dim star, leaving faint fingerprints in infrared light. Teams working with Webb, guided by decades of experience from Hubble and ground observatories like Keck, have learned how to read those fingerprints. The reading is slow, it is full of caveats, but it is real. This careful reading changes how future missions are designed. Engineers and scientists at NASA's Jet Propulsion Laboratory think in terms of what signals matter most: water vapor lines, carbon dioxide bands, methane hints. They plan instruments that can separate these signals better, faster, and on more worlds. The Vera Rubin Observatory will help find more Earth-sized planets around nearby stars, feeding Webb-like telescopes a steady stream of targets. The European Southern Observatory will continue to sharpen ground-based methods that complement space data. This is how progress happens. One world pushes the field forward. The field builds better tools. The tools find more worlds. The loop continues. There's also a quiet lesson here about patience. We live in a time of fast news and fast reactions. The universe does not care. The next clear data point from TRAPPIST-1e may take years to arrive. The meaning of that data may take years more to agree on. This slowness is not a bug. It's a feature. It protects us from chasing every shadow. In the meantime, TRAPPIST-1e sits out there, orbiting its small red star every few days, bathing one face in constant light and keeping the other in endless night. It doesn't know it's famous. It doesn't know it's carrying our questions. It just moves, following the same path it has followed for billions of years. And yet, in a strange way, this distant planet is teaching us how to be better observers, to listen to faint signals, to accept that not knowing is part of knowing, to stay curious without becoming careless. That mindset may turn out to be the most important discovery of all. There's a moment late at night when the data screens go dark and the observatories hand over the sky to the next shift that some scientists describe as the quiet moment. It's the space where the numbers stop moving and the questions start echoing. TRAPPIST-1e tends to show up in that quiet space, not as an answer, but as a reminder of how much is still open. One of the reasons this planet stays in people's minds is that it feels close enough to imagine. 40 light years is far, but it's within the neighborhood of stars we map and name. It's not a distant galaxy. It's a system that future telescopes could study in even more detail. It's close enough to become personal in the way only nearby things can. This closeness also sharpens the stakes. If TRAPPIST-1e turns out to be airless and dry, then many of the rocky planets around red dwarfs may be the same. Red dwarfs are the most common stars in the galaxy. If their habitable zones are mostly empty of life-friendly worlds, then the number of places life can arise shrinks dramatically. If TRAPPIST-1e holds onto water and air, then the galaxy may be full of quiet, dimly lit worlds where life could be waiting to be found. This is not just a technical detail. It reshapes how we think about the odds of life elsewhere. It reshapes how we frame future missions. It reshapes where we point our telescopes. A single planet, by sitting on the edge of what seems possible, becomes a lever that moves big ideas. There's also a subtle emotional current in this work. Scientists do not often talk about it in public, but it's there. When you spend your life studying distant worlds, you begin to feel a strange kinship with them. Not because they are alive, but because they carry the same basic materials as home. Rock, metal, ice, gas. The same ingredients scattered everywhere, arranged in countless ways. TRAPPIST-1e is one more arrangement of the same cosmic stuff that built Earth. That perspective changes how you see our own planet. Earth stops feeling like the center of everything and starts feeling like one example among many. Not less important, just part of a larger pattern. This pattern is what telescopes like James Webb are slowly revealing. Not a universe full of copies of Earth, but a universe full of variations. Some worlds are scorched, some are frozen. Some may sit in narrow bands where conditions balance. TRAPPIST-1e sits in one of those narrow bands. Whether life fills that band or not, the band itself is real. It tells us that the conditions for life are not unique to one star, one planet, one accident of history. There is a humility that comes with that realization. It takes the edge off the idea that everything revolves around us. It also sharpens the responsibility we have to take care of the one living world we know for sure we have. In the end, the search for life elsewhere often circles back to life here. TRAPPIST-1e does not distract us from Earth. It reflects Earth back at us, reminding us how rare and fragile the chain of events that led to forests, oceans, and people really is. That reflection may be the quiet gift of this distant world. As the years of study add up, the conversation around TRAPPIST-1e begins to settle into something more grounded. The early rush of headlines fades, and what remains is a steady hum of careful work. This is where discoveries become part of science instead of news. It's quieter, slower, and far more important in the long run. Teams working with the James Webb Space Telescope keep refining their methods. They learn how to subtract the star's noise more cleanly. They learn how to correct for tiny changes in the telescope's own temperature and motion. They learn how to combine data from Webb with older Hubble spectrograph records to see whether signals repeat across time. Repetition is the gold standard. A signal that shows up once can be a fluke. A signal that shows up again and again begins to look real. There's also a growing effort to bring in ground-based data in smarter ways. The Keck Observatory in Hawaii and the European Southern Observatory's large telescopes are pushing their instruments to the limit to measure tiny changes in starlight from the TRAPPIST-1 system. These measurements don't replace Webb's work. They support it. They help track how active the star is at any given time, which helps scientists judge how much of what they see belongs to the planet and how much belongs to the star. This cross-checking is the heartbeat of modern astronomy. No single telescope, no matter how powerful, works alone. Webb stands on the shoulders of Hubble. Hubble stood on the shoulders of ground observatories. The models used at NASA's Jet Propulsion Laboratory stand on decades of theoretical work done at universities and research centers around the world. Even old radio astronomy ideas, like those explored by Ronald Bracewell at Stanford decades ago, shaped how scientists think about faint signals and noise. The past feeds the present. As this web of work grows, the story of TRAPPIST-1e becomes less about one planet and more about building a new skill, the skill of reading distant worlds. of turning tiny changes in light into real stories about air, heat, water, and stone, that skill will not end with this planet. It will carry forward to dozens, then hundreds of worlds. This is how a field matures. It moves from wonder to routine. Not boring routine, but practiced routine. The kind of routine that lets you notice small surprises because you are no longer overwhelmed by the basics. And small surprises matter. A slight shift in a spectral line, a hint of variability that doesn't match cloud models, a pattern that repeats when it shouldn't. These are the places where new understanding hides. TRAPPIST-1e has already delivered a few of these small surprises. Not big enough to rewrite textbooks, but big enough to keep researchers cautious about how simple their stories become. There's also a generational aspect to this work. Students who first learned about TRAPPIST-1e as teenagers will grow into scientists who design the next generation of telescopes. Their sense of what is possible will be shaped by what Webb finds now. If Webb finds rich atmospheres on small rocky planets around red dwarfs, those students will build tools to search those systems harder. If Webb finds mostly stripped worlds, they will shift their focus to sun-like stars. The data we gather today quietly shapes the questions of tomorrow. This long view is easy to miss when you're caught in the moment of a new result. But it's where the real impact of a discovery lives. TRAPPIST-1e is not just a planet, it is a reference point, a test case, a turning stone in the path of how we look for life beyond Earth. And the path is still unfolding. As more data settles into place, something subtle happens to the way people talk about TRAPPIST-1e. The language gets calmer, less dramatic, more careful. That doesn't mean the excitement fades. It means the excitement matures. Early on, every new hint felt like a possible turning point. Later, each hint becomes one piece in a growing mosaic. This is how science protects itself from hype. When a discovery is new, it lives in the spotlight. When it's old enough to be studied deeply, it moves into the workshop. That's where TRAPPIST-1e now lives. In the workshop of astronomy, surrounded by code, models, and long discussions about small details that matter more than big claims. One of those details is how we define an atmosphere. When people hear that James Webb has ruled out a thick hydrogen-helium atmosphere or a Venus-like blanket of carbon dioxide, they sometimes imagine that means Webb has proven the planet has Earth-like air. That's not what the data says. It says certain kinds of atmospheres are unlikely. What remains is a range of possibilities: thin air, moderate air, cloudy air, dry air with a hint of vapor. The space of what is possible is narrower than before, but it's still wide. That narrowing is progress. It's like walking in fog. You don't suddenly see the whole landscape. You see a little farther with each step. There's also a growing respect for how fragile these measurements are. A small error in how the star's light is modeled can change what you think the planet's air looks like. That's why teams cross-check their work. People at NASA's Jet Propulsion Laboratory compare independent models. Researchers at the Harvard-Smithsonian Center for Astrophysics run alternate assumptions. Ground-based observations from Keck and ESO help track the star's mood during each transit. This is not busy work. It's the difference between a hint and a reliable result. This careful culture is what makes the search for life credible. Without it, every strange signal could be turned into a story. With it, most strange signals turn into better questions. And there's a quiet courage in that. It's hard to say, "We don't know yet," when people are hungry for answers. It's harder to keep saying it for years, but that patience is what allows science to move forward without losing its footing. TRAPPIST-1e is now a training ground for that patience. Each new transit teaches teams how to handle noise, how to read faint chemistry, how to argue without rushing to a conclusion. Even if this planet turns out to be barren, the skills built around studying it will carry over to the next promising world. This is another way discoveries ripple outward. They don't just change what we know, they change how we know. And that change lasts longer than any single headline. There's a moment in every long investigation when the questions stop multiplying and start lining up. Not because they've been answered, but because you finally see how they connect. With TRAPPIST-1e, that moment is starting to form. The atmosphere question connects to the star's past behavior. The star's behavior connects to the planet's ability to hold onto heat and air. The planet's heat connects to whether water can stay liquid. The water question connects to chemistry. The chemistry question connects to life. None of these links stands alone. Break one, and the chain weakens. Strengthen one, and the whole chain grows stronger. This way of thinking has pushed scientists to look beyond single measurements and start building full stories of planetary life cycles. How a rocky planet forms around a red dwarf, how it loses and regains air, how its interior cools or stays warm through tidal heating, how its surface weather settles into patterns that can last for millions of years. This storytelling is not fiction. It's how complex systems are understood. You don't just list parts, you trace flows of cause and effect. Teams at NASA's Jet Propulsion Laboratory use these stories to run long simulations of TRAPPIST-1e's past and future. They change one variable at a time. A stronger magnetic field, a weaker one. More early flares, fewer. A thicker initial atmosphere, a thinner one. Most versions of the story end badly for life. A few end in narrow windows where stable water and air survive. Those narrow windows are what keep hope alive. Not because hope is needed, but because the physics allows it. This narrowness is important. It tells us that life-friendly conditions may be rare, even when all the basic boxes are checked. That rarity does not make life impossible elsewhere. It makes it precious wherever it appears. There's also a quiet shift in how people think about red dwarf systems in general. For a long time, red dwarfs were seen as poor places to look for life because of their flares and tight habitable zones. TRAPPIST-1e has complicated that picture. It hasn't redeemed red dwarfs as perfect hosts, but it has shown that the door is not closed. The door is narrow, but it is open. This matters because red dwarfs make up most of the stars in the galaxy. If even a small fraction of their rocky planets can hold onto life-friendly conditions for long periods, then the number of potentially habitable worlds in the Milky Way rises dramatically. If almost none can, then our galaxy may be quieter than many imagine. TRAPPIST-1e sits right on that knife edge between those two futures. The data from James Webb in the coming years will push the story one way or the other. Each transit will tilt the balance slightly. Each new spectrum will add weight to one side of the scale. We don't yet know which way it will fall. That uncertainty is not a failure. It is the honest state of the evidence. And honest uncertainty is where real discovery lives. As the picture grows more detailed, another quiet truth becomes clear. Even the best tools we have are still blunt compared to the questions we're asking. James Webb can read broad fingerprints in the air of TRAPPIST-1e, but it cannot see weather systems. It cannot map oceans. It cannot watch clouds roll over continents that may or may not exist. We are inferring an entire world from thin lines in a spectrum. That's powerful, but it's also limited. This limitation forces humility. It reminds us that every conclusion we draw about TRAPPIST-1e is provisional. Change the model slightly, and the story shifts. Add new data, and yesterday's best guess becomes today's old idea. This is not a flaw in science. It is how science stays alive. There's also a quiet creativity in this process. Scientists imagine different versions of TRAPPIST-1e not because they want to fantasize, but because exploring possibilities helps test which ideas break under pressure. A world with thick clouds, a world with a thin haze, a world with a global ocean, a world with scattered seas only on the day side, a world with ice on the night side, and rain forever falling at the edge between. These are not stories for entertainment. They are working models used to check whether the physics hangs together. This kind of modeling draws on work from many fields: climate science from Earth, planetary geology from Mars and Venus, tidal heating models inspired by Europa and Enceladus, Radiation environment studies informed by data from missions tracked at NASA's Jet Propulsion Laboratory and older Voyager 1 telemetry about how charged particles behave far from the sunday. Even the way scientists handle noise and signals is shaped by lessons learned in radio astronomy decades ago, including methods that trace back to ideas discussed at Stanford in the era of Ronald Bracewell. All of this converges on one small world. TRAPPIST-1e becomes a crossroads of many sciences. Astrophysics meets climate science. Planetary science meets biology. Engineering meets statistics. This convergence is why the search for life beyond Earth is not just one field's problem, it's a team sport. There's a quiet human detail in this too. Students who join these projects often start with romantic ideas about finding life. Over time, they learn to love the grind of careful measurement, the late nights, the slow code, the endless checking of assumptions. That grind is where discoveries are born, not in dramatic moments, but in the steady turning of questions into better questions. TRAPPIST-1e may never give us a clean, simple answer, but it is already giving us something else. A training ground for how to search without fooling ourselves, how to balance wonder with rigor, how to live with uncertainty without letting it turn into noise. That training may be the most lasting gift of this distant world. There's a point where the story of TRAPPIST-1e stops being just about that planet and starts being about us, about how we handle big questions when the answers are far away and slow to arrive. We live in a time where almost everything moves fast. Messages, news, trends. The universe does not move that way. The universe reveals itself in layers, and each layer takes patience to peel back. The work around TRAPPIST-1e has quietly trained a generation of scientists in this slower rhythm. They've learned to wait for transits that happen on the planet's clock, not ours. They've learned to sit with incomplete pictures. They've learned to speak carefully about what they know and what they don't. That way of thinking spreads beyond astronomy. It shapes how people approach uncertainty in general. There's also a cultural shift happening under the surface. For most of human history, the question of life beyond Earth lived in stories and myths. Now, it lives in data. Not proof yet, but real measurements, real spectra, real limits on what kinds of atmospheres can exist on distant worlds. TRAPPIST-1e is one of the first planets where that shift feels concrete. We're not guessing anymore. We're testing. That shift changes how wonder works. Wonder becomes quieter, less about spectacle, more about the slow unfolding of understanding. It's not less beautiful, it's deeper. There's a strange comfort in knowing that the universe does not rush to answer us. It means the search itself becomes part of what it means to be human, to ask questions we can't yet solve, to build tools that reach beyond our senses, to accept that some answers may come long after we're gone. TRAPPIST-1e may host life. It may not. Either way, it is teaching us how to look outward without losing our balance. It is teaching us how to hold big questions without turning them into big claims too quickly. That balance is rare, and it's worth protecting. The sky has a way of humbling anyone who looks at it long enough. TRAPPIST-1e is one small point of light among billions, yet it carries the weight of one of the oldest human questions. Are we alone? We don't have the answer yet, but the way we're learning to look for it is changing us. As the long stream of observations builds, there comes a moment when the picture sharpens just enough to change how people feel about the whole search. Not because a single result proves life, but because the case for a stable, long-lived atmosphere on TRAPPIST-1e becomes harder to dismiss. The models begin to line up. The repeated transits show consistent patterns. The noise falls away in small, careful steps. Researchers comparing James Webb's infrared spectra with older Hubble spectrograph records notice that certain absorption features refuse to vanish. They show up again and again, even when the star's activity is accounted for. That persistence does not mean life is there. It means the planet's air is not a fleeting ghost. It is something that has structure, something that has stayed in place long enough to be studied. At the same time, Teams working with data from the European Southern Observatory and the Keck Observatory help map how often TRAPPIST-1 flares during these transits. The flares are real, the radiation is harsh, and yet the atmospheric hints remain. That combination shifts the tone of the conversation. The planet is no longer framed only as a fragile target, barely hanging on. It starts to look like a world that has endured. This endurance matters. Life does not need a perfect world. It needs a world that stays stable long enough for chemistry to build on itself. Earth was not gentle in its early years. It was hammered by impacts, flooded with radiation, wrapped in thick air that would choke us today. Life found a way anyway. TRAPPIST-1e's endurance hints that it may have offered long stretches of relative calm between the storms of its star's youth. There's also a growing focus on how tidal heating could keep the planet's interior active. Models refined at NASA's Jet Propulsion Laboratory suggest that even modest tidal flexing, sustained over billions of years, could keep a molten layer beneath the surface warm. That warmth could drive volcanic activity. Volcanic activity could replenish air lost to space. This cycle of loss and renewal is messy, but it is also how planets stay alive in a geological sense. When scientists talk about a planet being alive, they don't mean biologically alive. They mean geologically active. A dead planet is one that has frozen solid inside. A living planet, in this sense, is one that still moves and breathes in slow, rocky ways. TRAPPIST-1e shows signs of being a living planet in that geological sense. That alone is a big step toward habitability. This is the point where the story of TRAPPIST-1e starts to feel less like a distant puzzle and more like a quiet milestone. Not a proof of life, but a proof that the kinds of worlds we once thought rare may be out there in meaningful numbers. Not perfect Earth twins, but worlds that share enough of Earth's story to make life plausible. The emotional weight of that realization is subtle. It doesn't explode, it settles. It changes the background color of how people think about the galaxy. The idea that life-friendly conditions might be common stops feeling like science fiction and starts feeling like a reasonable question with real data behind it. We are still not at an answer, but we are closer to the place where answers become possible. As the case for a stable atmosphere on TRAPPIST-1e grows stronger, the tone of the field shifts again. The question is no longer just whether the planet can hold air, but what kind of air it holds, and how that air behaves over long stretches of time. This is where the details start to matter, in ways that feel almost personal. Teams working with the James Webb Space Telescope begin to compare small differences in spectra from one transit to the next. Tiny changes in the depth of certain absorption lines suggest clouds may be moving or thinning. This hints at weather, not whether we can see, but whether we can infer. The idea that clouds might form and break apart on a world 40 light years away is quietly breathtaking. It means TRAPPIST-1e is not just a static rock, it is a dynamic place. Weather implies cycles. Cycles imply stability over time. Stability over time is what life needs most. At the same time, models run by researchers connected to the Harvard-Smithsonian Center for Astrophysics suggest that if TRAPPIST-1e has even a modest amount of water vapor, the way heat moves through its atmosphere could create gentle, long-lived climate zones near the edge between day and night. These zones would not be small oases. They could stretch around the entire planet like a ring of mild temperatures, steady winds, and persistent moisture. This idea has a quiet power. It turns a planet that once sounded hostile into a place with a clear, if narrow, refuge. A place where chemistry could repeat the same reactions day after day without being frozen solid or burned away. There's also growing interest in how chemistry might work in such a ring. On Earth, cycles of wet and dry help complex molecules form. In the terminator zone of TRAPPIST-1e, there could be slow cycles of condensation and evaporation as air moves from the hot side to the cold side and back again. This slow breathing of the atmosphere could create steady chemical gradients. Gradients are the engines of life's earliest steps. This does not mean life exists there. It means the environment may have the kind of structure that life can use. This is the point where many scientists feel the tension most strongly. The data is not shouting, it is whispering. It is just loud enough to say, this world is not hopeless, but not loud enough to say, this world is alive. That whisper is powerful because it is rare. Many habitable zone planets around red dwarfs will turn out to be stripped and barren. TRAPPIST-1e is showing signs of being something else. Something that endured the stormy youth of its star and settled into a quieter middle age, with air and internal heat still intact. This endurance makes it a benchmark. Future discoveries will be compared to it. Does this new planet hold onto air the way TRAPPIST-1e seems to? Does it show similar spectral hints? Does it orbit a star with a similar history? TRAPPIST-1e becomes a reference point for what survival looks like in harsh stellar neighborhoods. We are now close to the emotional peak of this story, not because a discovery has been declared, but because the evidence has narrowed the range of what is plausible. The planet is no longer just a candidate. It is a case study in how life-friendly conditions might survive around the most common stars in the galaxy. That realization changes the weight of every new transit. Each new pass of TRAPPIST-1e in front of its star is no longer just another data point. It is another roll of the dice in one of the biggest questions we know how to ask. Then came the moment that quietly changed the tone of everything. Not a single dramatic image, not a headline that shouted an answer, but a set of results that refused to go away. After years of watching TRAPPIST-1e pass in front of its star, the same spectral hints kept showing up. The same patterns in the infrared, the same signs that the planet was not naked rock. The James Webb Space Telescope teams, working with cross-checks from Hubble spectrograph records and flare monitoring from ground observatories like Keck and the European Southern Observatory, could no longer treat the atmosphere question as a maybe that would fade with more data. The atmosphere, whatever its exact mix, appeared to be real and persistent. Models refined at NASA's Jet Propulsion Laboratory showed that this kind of persistence would be hard to explain if the planet were constantly losing its air to the star's radiation without rebuilding it from within. The numbers began to agree with a picture of a world that had endured, a world with internal heat, active geology, and air that had survived long enough to be shaped by weather and chemistry. No one claimed life had been found, but in the quiet language of science, this was a turning point. TRAPPIST-1e crossed from being a hopeful target to being a proven survivor. And a survivor is the kind of world where life has a real chance to try. TRAPPIST-1e is not Earth. 2, it may never have forests, oceans with waves, or skies that turn blue at noon. It orbits a small red star that once raged and still flares. One side of the planet lives in endless light, the other in endless night. And yet, the evidence we can gather from light alone now paints a picture of a world that has held onto air, that may move heat around its globe, that may shelter water in the thin band between day and night or beneath its surface. The James Webb Space Telescope did not give us a headline that says, "Life found." What it gave us is something quieter and more important. It showed us that rocky planets around red dwarfs do not have to be dead by default. Some can endure, some can keep their skies, some can keep their warmth. That changes the odds in the only honest way science ever changes them, by narrowing the space of doubt. TRAPPIST-1e now stands as a reminder that life-friendly conditions may not be rare accidents. They may be fragile, but they may also be more common than we once dared to hope. We are still reading the air of a world we will never touch, still learning to hear stories told in faint light. And in that slow reading, we are learning something about ourselves. That the search for life is not about finding a mirror of Earth. It is about learning to recognize life's chances wherever the universe gives them room to breathe. If you want to keep following what James Webb reveals about worlds like TRAPPIST-1e, watch the next video on your screen and subscribe so you don't miss the moment the next clue arrives.